My name is Eli, and today with Jean-Michel, we're going to talk about side channel attack using deep learning. We are both part of the Google security and anti-abuse research team. So side channel attacks is one of the most efficient ways to attack secure hardware because it targets the implementation rather than the algorithm, and usually implementations are harder to secure than the algorithm itself. So for example, last year, Johan Onik, I hope I pronounced his name right, did a side channel attack to recover the private key of the crypto wallet Trezor. That shows you the power of attacking the implementation rather than the algorithm. The sad problem with side channel attacks is they require a lot of domain expertise, and because they target a specific implementation, they're not very reusable. So if we have a super cool class of attacks and they are very specialized, the question is, can we do something about it? Can we make them more generic, and can we make them more reusable so we can reuse them across a wide range of devices? And the answer is yes. We do believe that deep learning, a form of machine learning, is the answer to make side channel attacks more reusable and more efficient. And we see a lot of you frowning in the audience like, AI, really? Again, one more talk about that. But trust us, actually, deep learning is a really, really good fit for script analysis, hardware cryptanalysis, and we're going to hope to show you that today. Fundamentally, the reason why AI is such a good fit for performing side channel attacks is because it's like template attacks, which are state-of-the-art, but on steroid. And what we mean by that is using deep learning helps us to address a few problems. So the first one is that when you use deep learning, you do not need any type of trace processing. So you don't have to cut them, you don't have to align them. The machine learning takes care of that, which is one of the biggest problems when you target secure implementation. The second thing is we can get rid of a lot of assumptions, such as the model of attacks. For the people in the know, like the Hamming weight model is not needed. You can directly target part of the algorithm directly with deep learning. So a lot of the human assumptions are out of the loop. And as a result, your attack is more efficient and easier to understand and carry. The third one is because deep learning has this ability to output probability, when we perform the key recovery itself, as we're going to show you, we can combine the deep learning probability to make a very nice and efficient probabilistic attack, which is something which is way harder to do with standard techniques. And last but not least, deep learning have a lot of metrics, and we can see the algorithm progressing, so we get a better sense of how well the algorithm is learning or attacking the hardware. And so we have way more interesting metrics that we can leverage. We're going to show that as well during the talk. So there is also a more fundamental reason why deep learning is such a powerful tool, and you keep hearing people saying deep learning, deep learning, deep learning everywhere, is because as far as we can tell, deep learning is the only technology we have, period, for any domain which actually scale with data and computing. So the more data, the more computing you have, the better deep learning become, and that's the only one we have. And that's really why the reason is of why it becomes so powerful. And you're like, okay, fine, I can see that for cat recognitions, but what's up with attacking side channel? Well, what it means is we can push further our attacks with more trace. The one thing is, the more trace you have about your implementation, and we can always generate more trace, right? It's just a bunch of crypto computation, the better it becomes. So we have a way, even for hard target, to scale up, because deep learning scales linearly. So all we have to do is generate more data, which is something which, for side channel attacks, is very easy to do when you have the board. So in a way, it's a perfect fit. So all of this will become, if it's a little bit blurry today, as now, don't worry about it. As we go through the talk, it's going to be more clear, and it will start to make sense. So today, what we wanted to do, because as DEF CON, we get rid of all the equation, we also get rid of all the complicated stuff, and we're going to focus on show you step by step how you can do it and show you it works. A lot of people have attempted it to use machine learning for side channel. Many people have failed. We failed a lot. It's been 2 years since we work on it, so we failed a lot. But when it works, and we wanted to show you step by step how to get there. So that will be very practical, no equations, no boring math, just straight up, if you were to code, that's what it would look like. And so we call those attacks side channel attack assisted with machine learning, also known as SCAAML. So during the talk, we're going to create SCAAML because it's a shorter and nicer name. This talk is based on a long project that we've been inside about 2 years ago with a bunch of internal and external collaborators around improving and hardening hardwares, crypto hardware we have, to provide the best hardware and most secure hardware we can. The slide, today we are making the slide public. They're already on the web. We also tweeted them with Jean-Michel, so you can have them today. Hopefully very soon we're going to give you also the code source that we use to carry the attack, so we'll run it yourself. And hopefully in the not too distant future, we'll also make available the whole research paper as well as all the data sets we collected and the model we trained, so you can actually reproduce our results. So, last disclaimer before we delve into the matter, we decided with Jean-Michel to focus on showcasing how to get the attack working, and as a result, we don't use state-of-the-art machine learning, we don't use state-of-the-art processing because we think it's more important to focus on clarity. We will succeed, to be clear, the attack works 100% of the time, but we wanted to make really a focus on getting you guys a clear understanding, so don't expect like super advanced machine learning here, but it's probably fairly advanced. Okay, so how it's going to go today? Jean-Michel is going to talk about what are side channel attacks, what is deep learning, so everyone on the same page, and then I'll come back and I'll talk to you how to use both techniques and combine them to do a SCAAML attack, and then we'll briefly talk about the research itself and what to expect next. Jean-Michel, take it away.
Thank you, Eddie. So first, let's step back and get the same definition on what we mean by side channel attack. So every time you do computation with an embedded device, a CPU, etc., it will result in some artifact created by this computation. And if you have a way to measure that and you have a correlation between those artifacts and a secret you want to extract, then you can conduct a side channel attack. It can be used to recover encryption key, which is the thing that we're discussing today. You can also, it has also been used in the past to perform blind SQL injections. You can also steal password and pins, extract crypto wallet private keys. It can be used for a wide variety of things. So we have a component, an electronic component. This component for the cryptography, we feed it with plain text data, and it has a secret key inside that we don't know and we want to extract. At the end, we will have some artifact, as I said, that we call leakage. And those leakage can be, for example, the timing. When you do a cache timing attack, if the data is in the cache or not, your CPU, your execution will last longer or not. And by deriving that, you can get 1 bit of data. You can also measure the power consumption during the encryption of the data, and that's the one that we are using on this presentation. Theoretically, you could also use the heat, but the problem with the heat is that it spreads and you have a huge latency. So despite using an infrared camera on a big CPU to see exactly which part is warming up to locate exactly where your crypto accelerator is located, the heat cannot be used to recover an encryption key as far as we know. And for this, we prefer to use electromagnetic emission instead of the heat, which is more precise and doesn't have the same side effect. But we're not using it on the attack we're showing you today. So side channel attack in a nutshell. We do some encryption with the microprocessor. We're measuring the current consumption with an oscilloscope. We accumulate that over time with different plain text. And we do a template attack for the state-of-the-art attack. A template attack is still an attack that requires a powerful attacker because most of the time, to train a template attack, it's a probabilistic model that you have to train on what is called a white box chip. The white box chip, is a chip on which you can control the encryption key. You train your probabilistic model and then you apply it on the chip where you don't know the key and you want to recover it. And at the end, your probabilistic model will give you the AES key. So as we see here on these theoretical curves, not the real ones, we can see that most of the time the trace overlaps, but on the top of the curve, we have some discrepancies. And those discrepancies hopefully will happen on a clock signal for the CPU, which means that it's the register which are changing values, creating different kind of power consumption at a given time for the different bits that are set. And that's the kind of thing that you're looking for. And ideally, if this point at the time only relies on a part of the plaintext that the attacker controls and a part of the key that you want to recover, this is an attack point. Here we see a full trace of a lightly protected AES trace. It's AES 128. And if we take a deeper look at this particular box, we can see some humps and some repeating patterns. And if we count them, there's actually 10 humps, and that exactly corresponds to the 10 rounds of AES 128. So you see that it can be also very visual. This is how we were doing that in at the beginning of the project. It was sitting on the corner of my desk. So we have a PCB which has a target chip. That's the one containing the encryption key that we want to recover. Here we have a differential probe that is measuring the power consumption over time. And it's connected to the oscilloscope that is here. And here we have the communication interface to be able to feed the plaintext to the chip. And that's all it takes. If you want to start, New AE Tech and Colin, who is sitting on the second row here, is the creator of Chip Whisperer, which is a very cheap and easy way to start with side-channel attacks. On the board, you have all you need. You have an oscilloscope, you have the communication interface, and it has multiple targets to try this. If you're interested, we invite you to talk to Colin. He has a few Chip Whisperer Nano that he can give to some of you. But most of the time, the limitation of the Chip Whisperer is that it's feeding. The clock that it generates and the sampling rate for the oscilloscope is limited. And when you're attacking more secure elements, most of the time they won't allow you to feed any clock to it or to slow down the clock, which means that you will need a very high sampling rate for your oscilloscope. And for this you will need a real oscilloscope, but the software stack provided by the Chip Whisperer is already compatible with that. Also, during our paper, we do asynchronous capture. So the Chip Whisperer usually works with synchronous capture, which means you have one single clock that you feed to the chip, and the oscilloscope will capture the data exactly at the right amount of time. Most of the time, if you use an external oscilloscope, this won't happen. You will have exactly what you see on the screen. You will have different clocks, one for the oscilloscope sampling and one for the CPU, and they will be out of sync. Which means that if you want to sample in this setup, you need the oscilloscope to run at least 4 times faster than the clock of the CPU you are attacking. And that's why our setup evolved over time during the project, and right now we're using a Chip Whisperer Pro, which is a bit more expensive than the Chip Whisperer Lite or the Chip Whisperer Nano kits. And we use a Picoscope 6000 series. This is not an advertisement, the talk is not sponsored, this is just what we use so that if you want to reproduce the setup, you know that this works. And the reason why we pick the Picoscope 6000 series is because it can sample at a very, very high speed rate. It can go up to 5 giga sample per second, so we can attack a chip that is running at 1 gigahertz. And it also has very big memory. It can store up to 2 giga sample in memory, and it's very important when you start attacking asymmetric cryptography like RSA or elliptic curve, because the traces are really big. So now let's move to what is deep learning. Deep learning is basically a neural network, but with many layers, and they are stacked together like pancakes. So at the beginning you have a series of neurons mimicked with the biological one. The number of neurons that you have defines the width of your layer. Then you start stacking them like pancakes, and it creates a depth on your network, hence the deep learning. Then you add an input layer to process your input, and one for the output to do the prediction, here between dogs and cat. When you want to use the machine learning, you feed, for example, this image of a puppy. You feed it to the input layer, it will activate some neurons, they will propagate their predictions to the next layer and the next layer, And at the end of the output layer, it will issue the prediction whether this picture was the picture of a dog or a cat, and here it will say that it's a dog. But when you have different use cases, you will need to use different types of layers, different types of network architecture, so it can make things quite complex very quickly. So what do you need to train a deep learning model? Basically, TensorFlow will allow you to write and to train your model. It's written in Python. But it's very, very slow to train on a CPU, so don't try that. You will need a hardware accelerator for that. You can use either a GPU, or if you use on Google Cloud, we have what we call TPU, TensorFlow Processing Unit. And this is a dedicated ASIC that is there for, especially for TensorFlow and deep learning trainings. The demo code will try to make it available as soon as possible on Colab. Colab is basically a Jupyter notebook but hosted in the cloud, and it already comes with the TensorFlow already set up and free GPU, TPU time computation. And now I will give back the mic to Ellie, who will guide you through your first SCAAML attacks.
Thank you, Jean-Michel. All right, so now that we have the basics done, we're going to try to see how we combine both and making it work in practice. So, as I said, our goal is to get you through the attack step by step and try to provide as much information as we can so you can reproduce and understand what's going on. So the first thing to decide is what we're going to attack. And for this presentation, we selected a chip, which is the STM32F415. This is one of our favorite boards because it supports a lot of software implementation, but also have hardware implementation you can run on it. So we can compare hardware protected AES versus software ones and try to test many of those. And for the implementation, we're going to use TinyAES, which is an unprotected version of AES because that's the easiest one to attack, and that's the one where you're going to get the best result. So there's one downside to it that I'm going to explain a little bit more in detail later, but because it's software, it's very slow, so those traces are very big, and that make it harder to train because you need more GPU memory. Okay, so Jean-Michel showed you earlier what is a SCA game plan. So we're going to upgrade it to making it a SCAAML game plan. So same as before, we do encryption on the chip. We hooked our chip whisperer and picoscope, get the data, feed it to a neural network, and we need to talk about how we're going to train that thing. And then we'll have to combine those things and do some sort of inversion and a little bit more extra work to actually recover the actual key. And if everything goes well, you get a AES key, or in our case, we'll try to get many AES keys. All right, so as I mentioned, TinyAES is great. It's software, it's open source, you can have it. However, it is super, super slow. And what I mentioned that is because it's going to take about 80,000 points as input. It's fairly large. It's actually larger than most of the images we feed into a neural network for recognition of images. So we will have to do a little bit of different type of architecture to kind of reduce the amount. For the demo we're going to provide to you on Colab, Colab only has 20 gigs of memory. That seems a lot, but actually it's not for deep learning. And so what we did is we also have another data set coming out, which is Colab specific, where we basically took 1/5 of the trace, so you can load it in memory and play with it. So you can do that. It's more efficient because you have a fewer points to process, so you can put more in memory. The problem is we are violating our first promises, which was you can do on full trace. So if you want to do on full trace, you need a lot of memory and you need pretty beefy GPUs. We use GPUs which have between 12 and 16 gigs of RAM when we train them on the real thing. All right, so what deep learning model architecture do I need? All right, that's the question is like, okay, I have my data, what do I process it with? Well, the obvious answer is we're going to do the same thing what we use for speech processing and image recognition, which is what we call a ConvNet, also known as convolutional neural network. So the reason why those are better is because they slide across the data, and so you don't have to process all the points at once. So the number of parameters and connection is lower, and because we really want to have locality, right? What we want is to feed them and then stack them. So that's our favorite network of choice. However, if you want, you can also use, for people who like deep learning, use LSTMs More precisely, GRUs works pretty well too if you stack them. So you can use those other architecture, but this one works well. It's fast, so that's our favorite one. What does it look like, right? So a little bit of code. I promised no equation, but I didn't promise no code, so you guys have a little bit of code. This is a TensorFlow 2 code, or Keras, for those who like that better. And the idea is we have a bunch of constant, which is just setting up our network. The important one is the last one, called pool size. So what pool size will do is by how much are we going to combine as the first layer, which is going to be in a second. So first we take the input. So we convert it basically as an input for our layer, for our networks. Then we do a max pool. So what does the max pool do? The max pool do the following. It takes sliding windows, so we put 4, and it's going to take the maximum value for each of those 4. So in a way, it's basically shrink down your trace from 80 point to, well, 20,000 point. And then you tend to process them with convolutional layers, which are here. They are not the same as images because they are one dimension. Why one dimension? Is because we have a trace of 1 point, right? This is just the value of the current. We don't have 2D like images, X and Y. So that's why we use 1D. For those who like machine learning, you might already recognize that we don't use a normal convolution. We use the convolutional blocks where we did put batch normalization in the middle. And the reason for that is it speeds up the training. And then we keep doing a few of those. I think in that example we did 5. So we do 5 times those 3 layers, so you already have 25 layers here. So that's why we call it deep learning, is because we already have about 30 layers at that point. Then we do another max pool, so that's the final one, where basically we have all those convolutions, which create a lot of depth, if you would. Like a number of filters is a depth, and then we combine them to find the maximum one for each of those points. And then we add a little bit of dropout and a dense layer to connect everything and do our prediction. And our prediction, which is the last layer, that's the output of your layer. If you remember the cat and dog here, we don't have cat and dog. What we have is we have 256 values. And I'm going to explain a little bit more what they are in a minute. But basically, we have 256 values that the network is providing to you. The important point here is you might consider the idea of using sigmoid, which is another way to do it. If you do that for deep learning and for side-channel attack, it's a horrible idea. It's a horrible idea because we have only one value which is true, right? If you try to predict an image, you can have a cat and a bench and something, so you have multiple classes. In our case, we have a single class which is true, which is a value you want to predict and nothing else, so you have a lot of zeros. So basically, every time what the machine learning is going to learn is if I have 256 zeros, I have 99.9% accuracy. So your model showed nothing for a very long time. So that's why you should always use a softmax. We try both, and really that's the best way to do. So don't use sigmoid if you try that at home. Okay. So now the one thing I haven't explained is like, okay, so I have a model, I have data. What am I trying to predict? Well, that's where things get complicated. So this is AES. This is a round of AES, to be precise. We're going to talk about the first round of AES. And the question is, what do we do? So as Jean-Michel explained, we are doing power consumption. And the question is, why is power consumption reflecting the key, right? What happened is, if you want to set a bit in memory to 1, you need power. If you want to set the bit of the memory to 0, you need no power, right? So basically, you need more power if you have 8 bits at 1 than if you have 4 or 2, right? So basically, we need to find every point in the algorithm where there is a shift of some memory, and those are going to be where the power differences will going to kick in, and we'll have some sort of differentiable place to look at. Fair? Okay, so where are those? Well, first, when you feed the key. You feed the key in memory, you load your key, so your key is loaded, so that's the first point. Then you have to do something where you combine the key with the plain text, so that's an XOR. So when you do this combination, well, again, you might have also some loading there. Then you have the S box, and after the S box, again, you go out of the S box where substitute things. Again, you're loading the new value in memory, so again, a third at that point. Then you have one more, which is before the key scheduling, and one after the key scheduling. and then you repeat that 16 times because, well, there is 16 bits for each of those things. And then in a theoretical model, you can repeat that 10 times because there is 10 rounds. However, there is only 2 rounds you can use to recover the key directly, which is the first one and the last one. The one in the middle are way more complicated, while in theory, in cryptography, we consider them as an attack because they leak stuff. It's really hard to exploit. It might be possible in the future, we might be able to do stuff, but for now, we're just going to focus on the initial round, where you have only 3 places or 3 type of prediction you can do. So the first one, as I mentioned, that we call AP1, is you just predict the key. You say, hey, give me back the value of the key. That's the easiest one to do because, well, that's a direct prediction. The second one is please predict the value of the key and plain text, and that's why I explained you need a little bit of computation after the prediction, where you have to, well, de-XOR the plain text. So this only works for attack where you have a chosen plain text, which is the one we're demonstrating today. And finally, the last one you can do, which is also a very common one, is you go after the AES box. So in that case, you have to invert the AES box, invert the XOR, so it's a little bit more computation, and you have that. Don't worry about it. We have implemented all of those 3 types of attacks into the code we're going to give you in a few, hopefully soon, and you will be able to run them. So where does it leave us? That leaves us to this idea of we take the power trace, we feed it to the network do all those crazy layers I showed you, and output a value through a softmax. So what is a softmax? Basically, the softmax is you take your 256 value and you say normalize such as the sum of all those values is 1. The reason of 1 is because it makes a very nice smooth probability, and we constrain the output so every prediction is comparable, and it's going to be important later. It's a standard technique, by the way, to machine learning, so this is already built in. And so we make 256 value prediction by the model for each attack point value. So if we were to target the key, each of those output is the value of a byte, the value it can have. So last thing I need to tell you, and this is where it becomes not complicated, but it's a little bit different from what you expect, is we do 1 byte at a time. So if you were to attack a full key, what you will do is you will have to train 16 models. 1 for each byte of the key, 1 for byte 0, 1 for byte 1, 1 for byte 2, 1 for byte 3, and so forth. And you're like, why? Well, we have 256 value for the first byte, and then you repeat that 16 times. So we don't want to have like about 3,000 value to predict. That's not useful. We could, but it also push the model to have higher capacity, right? Because you have now, the model have to learn all the non-linearity to predict all of those value. So your model is going to be bigger and it's going to be harder to train, so it's easier to have 1 model per key. And a question that we've been asked quite a bit is there any bytes which happen to be harder? The answer is most notably no, but in some implementation it seems that the bytes which are at the border, which is 4, 6, and 4, 8, and 12 are a little bit different because of the power of 2. So in some implementation they seem a little bit weirder, but they all work the same in the end. Okay, so you do that, you're ready, you have your code, you click fire, and then you wait because it takes hours. Sorry, it's not very easy. Training a machine learning model takes time. You have to train on about 50,000 examples. You come back and you cry. It doesn't work. We lied. We actually, the model I showed you, I lied. It just doesn't work. And then you're like, okay, should work. Why isn't it working? Well, you try many of those and none of them works. And that's where most people have stopped, and we have countless people say it doesn't work. And that is true. Learning crypto is hard, and you're going to fail a lot and a lot and a lot and a lot. And for about a year, we had only failure to report. We know it should work, we just don't know why. And to be honest, we still don't know why. However, we have a way, right? So how do we deal with it if we can't find it by hand? Well, the answer is, don't do it. Rely on hypertuning. So hypertuning is the idea that you are fuzzing your model architecture to try to find the optimal one, and you try to do it until you find the right one, and you just throw at it more CPU and more computation. So even for this simple example, We had to do that. I really wish I would show you a model which is super easy to understand, that will work just right. I don't have one. What I did is I trained about 1,000 models on Google Cloud using Kubernetes and Keras Tuner, which is the hypertuner we developed for TensorFlow 2 with the TensorFlow team, and I selected one which works. And as I said, we have a super amazing model to show you. However, it's not going to be as simple as the previous one. We're like, okay. So you brace yourself and like, okay, what do you mean by more complicated? Well, this is a simplified view of it. It's not that bad, kind of. It's a few hundred layers now. So same as usual, we have the input. And then we have a max pool. The max pool is 6 this time. Don't have the space to put everything. Then we do 2 normal convolution, which is help us to decrease the number of points and increase the number of filters. Then we do what we call residual blocks. And so the residual blocks, the idea is you are adding shortcuts into the network to actually force the gradient. So the gradient is when you make an error, you backpropagate the error to the network. And one thing we found is the gradient is vanishing a lot when we do training on crypto. So use a shortcut to retain the gradient. This is something they also do in images. It's called RASNet, residual blocks. So you do a few of those, and here what happens is you decrease the size of the trace and increase the number of filters. So decrease the width, increase the depth, and then you need a lot of residual blocks. So that's not the same. Why is it not the same? Well, in that case, the number of points do not decrease, but you increase the depth. So basically, you do a combination of all of those, again, with residual. You do a max pool, you do a dense, you remove the dropout because it doesn't help at all, and you do it on 256 layers, and you have something which works. And that is a simple example I can show you which works. And I cannot find it by hand, and you're like, Eli, what is intuition? The answer is, I have no intuitions. Absolutely zero, don't know. For some reason, it's very, very finicky, and we have some which works, so empirically that works. The intuition is not easy to get. And the cat is happy, and we're happy too, because now we have something to show you which works. How well does it work? Well, this is the trace out of TensorBoard, and the model is going to do nothing for a few epochs. So also another thing, don't get discouraged if you train model for crypto. For 4 or 5 epochs, the thing do nothing. I mean, it kind of goes to 5% maybe, and then go down, go up. It's not really, really good. And then it starts to learn, and then it's going to spike at 35% accuracy around 30 epochs. 5 minutes per epoch, so about 2 hours later you have your result, and then the thing collapses. So this is validation accuracy, means these are on traces that we haven't seen during the training. These are traces we use to monitor the generalization of the model. And yes, it's going to collapse, and all our model collapse at the end. We're not sure why, but that's what happened. And then you get that model, and you checkpoint it, and you save it, and that's your model. We also try data augmentation. Sometimes it works, sometimes it does not. A lot of people say it does. It kind of, except if you make it wrong. It actually completely destroys your ability of your model to learn, because it seems to destroy some of the nonlinear correlation you need. So do not use data augmentation unless you have to, or you feel you want to push further and have a good baseline. So let's go back a second to what I mentioned earlier, which was we have multiple attack points, and answer a question, which is, does it make a difference whether you attack the key XOR the plain text, or the output of the S box? And the answer is yes, it does. If you try to predict the key, it just doesn't work. If you try to predict the plain text XOR the key, it actually works really well. So the one I showed you, 35%, works really well. Spike a little bit after the sub-byte in, which is plain text XOR the key. So both works in that implementation. However, if you were to use something else, it might completely be different. It actually depends on implementation. It is dependent on where is the leakage coming from, and so you don't know where the leakage is coming from. So that's another reason why we need to scale computation, is we don't know. So let's finish saying by, okay, so now we have a working model. How do I recover the key? Well, as I said, we're going to make this very nice probabilistic attack using our predictions. And the way it's going to work is we're going to take a trace, it's a model which is trained, and it's going to say, here are my predictions. And we're going to accumulate them. So we're going to do it on a few traces. You can go to 1,000, 2,000, 3,000, but really we don't need that much. And then you're going to sum them, and you're going to take the maximum value would be your best predictions. What is very interesting about deep learning is we also know what is the second value, and the third value, and the fourth value. So even if you don't get it right, you can brute force. And it's very easy to brute force because you know in which order to test each of the bytes, because the machine learning will tell you which one are the most likely, the second most likely, the third most likely, and this is something which is unique to deep learning compared to template attacks. Also, we cheated here again. We use log 10 to accumulate traces because that's the correct way to do it mathematically, just for people who try to do it. And then an important thing we found out that very, very few people do in the literature is making sure it works across chip. And the way we do that is we train the model on one chip, but then when we do the real attack, we do it on a second chip because we want to make sure that the model generalizes around the difference that there is between chips which are from the same family, right? You don't want to test on the same chip because all you learn is a model which might be dependent on the specific chip you got. So we do two chips, one for training, one for testing. And then the last thing we need to mention is, okay, so we have our data set on our second chip. How do we evaluate the effectiveness of the attack? So there's 4 ways. The first one is top 1 accuracy, which is how many of your predictions are in the top 1. Top 5, how many predictions are in the top 5. Then mean rank, what is the mean rank of your key? Remember, you have 256 predictions. Crypto is supposed to look like random, so 128 is your baseline. And what is the max rank? So the idea is the machine learning have shifted the search space and reduced it. So the max rank gives you some of those ideas. Now, one thing we do, which is also very different, is we try to recover 100 keys. And the reason to recover 100 keys is because we want to make sure we can recover a wide range of keys rather than one specific key to make sure we generalize. So the holdout data set is made of 100 keys, and we use 300 power trace that we can accumulate and see how well we do. So, do we do well? You know, the cat is very anxious. He tries, and then, yes. Actually, you can recover 100% of the TinyAES key using the attack I showed you. Moreover, so 100%, all of them are 0 because, well, we have all of them. Moreover, what is perhaps more impressive for people who know side-channel attacks is, while the model has 30% accuracy, and that's a very deceptive metric, we recover 100% of the key with no prior processing, but also in at most 4 traces. When you template attack, we ask Colin, it's about 5 to 6 traces. So you are better than state of the art even with a simple model. And perhaps more impressively, if you were to use a single trace, you'll get 81% of the key correct. And that shows you how much more powerful deep learning is to do side-channel attacks, at least on AES, and that's really why we claim it's going to be the future of it. And that's why we try to get more people excited to work with us on that. So to wrap up, because I think we have 2 minutes left, we need to deal with also protected implementation, which is not the focus of this talk, but are a very active field of research. And to deal with those things which have actually no pattern, you need something way more. And that is what we are doing next, which is we have built a large data test bed with 6 implementations, including a few hardware ones and protected ones, collected over 9 million sample traces, and trained over 5,000 models. And we hope to make all the results as well, all the models that we've learned and all we learn into a paper soon, so you can share our results, get you to reproduce, and help us work on the next step. So the takeaway is deep learning is the future of SCA. I hope we convince you by the result and the advantage of deep learning over traditional technique are really, really big. And so it's a big leap. It's very different from what we did before, but that's really worth it. It is really hard. You fail a lot, and so don't get discouraged. You really need automation. We don't know how to do it without automation. We're not making it the pitch of like, hey, let's use a lot of GPU. It's just like we don't know how to do it otherwise. This is how we found our way in the last 2 years to be doing it. And we really believe it's the beginning. We are aware of other researchers working on symmetric, asymmetric analysis with deep learning and finding great success. So that's really where the thing is heading. And really, If we can automate such an attack, then we'll be able to go back and focus on designing secure implementations of crypto that we can test very efficiently. So we can provide the world way more stronger crypto, which is really like strong implementation, which is really what we want. We really want to provide very strong chips that we can trust to put our secret in it. So thank you so much for attending today. We're really happy you took an hour to be with us. We hope that some of you are inspired to do some of this work with us or on your own. We put a slide today as you are here. Thank you so much.